Hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of us to my discussion for today. And we are going to look at a concept under motion, which is basically the concept of free fall. Now, this is going to be one of the kind of motions which we are going to describe. And this is going to be a fall which is going to be under the influence of acceleration of the concept of gravity. Now, we have mentioned this specific concept of gravity from our previous discussion. And of course, we talked about this one in details, especially under the concept of a description of the motion of an object, whereby we came up with a range of formulae which are going to assist us in trying to describe this specific aspect of free fall. And therefore, the concept of a free fall is a fall due to the influence of gravity. And I'm going to use this specific illustration of my two sets for A and B in order to, of course, evaluate the concept of a free fall. And we're going to look at various aspects of describing, especially the concept of velocity, the concept of displacement or distance. And of course, we're going to look at the concept of acceleration. And in this case, we shall look at the range of acceleration, which we see on the concept of a constant acceleration and instantaneous acceleration for velocity and acceleration in this specific respect. Now, we're going to see that there's going to be a unique behavior which we are going to witness, especially in treatment of the four kinematic equation which we had derived in our discussion on the concept of finding motion of a body. And these are going to be assisting us in trying to deal with other scenarios which we are going to come across, especially under the concept of free fall. Now, we're going to look at this specific concept from the first discussion we had on this specific kind of motion, whereby I said that we can consider an object that is going to be moving with a velocity, initial velocity of v naught, given as that one. And of course, this is going to be moving at a specific time interval given in terms of delta t. Now, if we are going to find the gradient of this specific graph, then therefore that's going to be giving us what we refer to as a constant acceleration. Now, in this case, we can see that from this specific definition of acceleration, we are going to have a representation of this acceleration given in terms of change in velocity over a change in time. And this, of course, is going to be giving us the aspect of delta v equivalent to the product of acceleration and change in time. Now, in this case, we had said that if we consider the change in time from the final to the initial for this specific set of a graph, then therefore we're going to have this one giving us the product of delta t. So we are going to consider the change in time between, perhaps let's give this one as at t1 or at t naught, and then we shall have this one at t1 given as that one. So we're going to have delta t given in terms of t1 minus t naught, but we can indicate this one in terms of t given in terms of t1 minus t naught. So implying that delta t can be given in terms of this t given as that one. So if we are going to consider this specific motion in one direction, or rather given in this specific direction of x, then we can represent this one in terms of velocity initial given as that one, velocity final given as that one, velocity initial, and then this one is going to be given as this. So we can have this specific velocity initial given in terms of ux, and we can have a final velocity, this one given in terms of vx. So this is going to imply that we can have a representation of this specific formula in terms of this is a particular representation of vx is vx minus ux is equivalent to a, and I've said this delta t is going to be given as that one. So this is going to be acceleration in this particular direction of the velocity, whereby it's going to be along the x component. So we're going to have vx, which is a final velocity, being a summation over ux plus ax t given as that one. And this gave us the first kinematic equation which we had derived from our previous discussion on the concept of describing motion of an object. Now, this is going to be forming one of the fundamental equations which we are going to require in order for us to describe the concept of a free fall. And in this case, we had also looked at the concept of the distance it traveled, which is going to be, of course, one of the ways in which we are going to be finding an equation for that one. So we said in the first case, for the first illustration of a motion of this specific object that is going to be accelerated in a constant way, as such, we had described velocity in terms of change in, of course, or the total displacement divided by the time, or the total distance covered divided by the time given as that one. So therefore, we can evaluate average velocity in this specific case using the total distance traveled over time. So which means we are going to have this specific aspect of the total distance traveled given in terms of velocity average times change in time. So this one implies that we're going to find this aspect of velocity average by the initial velocity plus the final velocity divided by 2, and then we're going to have this one times the time taken. So this is going to be giving us the displacement along the x-axis. And if we evaluate this one, we're going to see that we are going to have a representation of the total distance traveled using this specific illustration for the of course, the product of the initial speed times time plus half the product of a acceleration along this specific axis for x times time. And this gave us the second equation apart from. So this was our first one. This was our second one. And then we said that, of course, we're going to obtain the concept of this specific representation for final velocity in another version. And that's going to be giving us one of the ways also which we're going to be representing this aspect of a free fall. So from this specific discussion for the formula which we are given in terms of Vx is equivalent to Ux plus At. So we have decided that we can find time from this particular representation by having it as the difference between Vx minus Ux, and then this is going to be divided by Ax. So in this case, we can have T being a subject of this specific displacement using Ux into Vx minus Ux all over Ax. So this is going to be forming a substitution for T for this first and second aspect in this particular case respectively. So this is going to be T, of course, so this is going to be an evaluation of this one, which is going to be giving us T, the square of T. So in this case, we're going to have this specific aspect whereby we're going to have this particular equation giving us. So basically, this specific adjustment was done with respect to this particular representation, which are given, whereby Vx is going to be represented by Ux plus Axt given as that one, and this is going to be giving us the product of our second evaluation. So in this case, we're going to consider this, of course, third equation, which is going to be assisting us in describing the concept of a free fall, whereby I said that we're going to take this equation and have this aspect of a T substituted from the first equation, which we had mentioned. And then we're going to have this one plus a half Ax, and then we're going to have this T given as Vx minus Ux all over Ax, and then we're going to have that one given as the square. So this is going to be T squared, and then therefore this is going to be forming our Sx, or rather, in evaluating this one, we're going to have a Vx squared equivalent to the value of the square of the initial velocity plus the product over 2ax sx given as that one. And this, of course, are going to play a vital role in assisting us trying to describe this free fall. So in this case, for the three equations, for the first one, the second one, and the third, these are going to form kinematic equations apart from the fourth, which I'm going to introduce later. And they are going to assist us in trying to describe either the acceleration, which is going to be either positive, or acceleration due to gravity. In this case, we have considered the various aspects of acceleration given in terms of Ax. But in this case, we're going to consider acceleration due to gravity for such a kind of an object given in terms of this specific representation. So our displacement is going to be along the y-axis for this free fall. And then we're going to see that acceleration is going to be acceleration due to gravity. So we're going to give this one in terms of g. And then we shall have this specific initial position, which is going to be the point at which this specific object was released. It's going to be 0. And this is going to be forming our ground level given as that one. So this object is going to be moving towards the ground level given as that one. So therefore, from the three kinematic equations which I've just derived from my previous discussion, we're going to have this particular velocity along the y-axis represented in terms of the initial velocity along the y-axis, and the product of this specific gravitational, of course, the first acceleration due to gravity times the time given as that one. So this is going to be forming our first equation for description of the movement for velocity along the y axis given in terms of that free fall. And then we're going to have the total distance covered represented in terms of the initial velocity and then times time times half the value of velocity and the square of time. And this is going to be forming our second equation given as that one. And then we shall have this specific value for the square of velocity given in terms of y squared, and then minus the product of 2gs given as that one. So this is going to be s, which is a displacement along the y. So this is going to be forming our third equation, which we are going to rely on in describing the final velocity of this specific aspect of free fall. And then lastly, we're going to have this specific equation that is going to give us the value of the total distance covered by having the average velocity times time. So this is going to be the initial velocity along the y, and then the final velocity along still the y axis, and then this is going to be given times time. So this is going to be forming our fourth equation. So in this case, we can see that from the previous equations which are described for the kinematic equation for the first, second, and third, these are going to be analogous equation, only that we are going to consider in this case the element of gravity given in terms of a negative value given as such. And this is going to be assisting us in trying to describe this specific aspect of acceleration due to gravity. Now, this is going to be, of course, a contrast with the last one, which, of course, is going to describe the concept of displacement, or rather the distance covered, which is going to be average velocity given in terms of the initial and final half of that one times the time given as that one. So these are the specific equations which we are going to use in trying to solve for various problem sets. Now, with the specific characteristics which we are going to come across, especially in trying to describe the concept of a free fall, whereby we're going to see that the motion of a particle in this particular case is going to be, can have a zero velocity, but yet it's going to be accelerated in this particular form. And we're also going to see that this specific case, we can as well consider the concept of a circular motion. So in this case, we have said for this kind of a motion in free fall, a particle can have a zero velocity, but it's going to be accelerated. But for circular motions, we're going to see that particles are going to travel with a constant speed, but they can as well have a velocity. So in this case, it is going to be associated with a change in position. And this particular velocity are going to be described as the tangential elements along this specific part of our travel, given in terms of those particular representations. So therefore, they are also going to be experiencing an aspect of acceleration. Now, in this case, we can have velocity in one direction and acceleration in the opposite one. Now, in this case, this is going to be describing especially some of the motions which we are going to come across. But of course, I've mentioned some of them in my previous discussion on the concept of a pendulum. So if we are trying to describe a pendulum in this equilibrium position given as that one, we can have it perhaps given as well in the direction given as such. So if we are going to try and describe the velocity component and acceleration in this particular case, now this is going to be one of the examples whereby we're going to have acceleration and velocity having, of course, opposite kind of direction as I've mentioned. So we're going to see for this case, we are going to have two endpoints, whereby this is going to be a displacement towards the right, forming the first endpoint, or the initial position. This specific point is going to be forming one of the endpoints. And then the final position is going to be another endpoint given as that one. So a displacement from this specific position to the another one, and then back is going to be, of course, displaying this aspect of velocity and acceleration, whereby we're going to see that at this specific point, apart from the endpoint, this is going to be describing the equilibrium position, whereby at this point we're going to have our acceleration given in terms of zero. But in contrast, we're going to have what we call a maximum velocity at this specific point. So in this case, for the endpoints which we are going to see for this kind of a motion, we're going to have a maximum force being experienced at this specific point. But we're going to see that this specific point as well, we're going to have what we refer to as maximum acceleration. So in this case, we can see that there's going to be a variation given for acceleration and the velocity. But in contrast with that, we're going to see that the velocity at this specific point is going to be equivalent to zero. So this is going to be the case for this other endpoint which we are going to see for such a kind of a motion which we are going to see for a single pendulum, whereby acceleration and velocity are going to be having a different description for a direction given as such one. So this is going to be especially the case for the such a kind of a sinusoidal behavior for motion of a pendulum, which we are going to come across. Perhaps we can wrap up this one with a simple example, which perhaps I think we'll just tackle a number of them in our subsequent discussions, which we're going to use in trying to solve this. So in this case, I just read it through a problem set. We extract the information and try to use the examples or the evaluation which we have done in order to solve it. So in this case, I just read it through the question, which says that a feather is dropped on the moon from a height of 1.4 meters. The gravitational force, the gravitational constant on the moon is 1.67 meters per square second. Determine the time for the feather to fall to the surface of the moon. So perhaps I can give this one in terms of an illustration. So we're going to have our moon, and this is going to be forming our feather, which is going to be dropping towards the surface of the moon. And the distance between the feather and the moon is, of course, 1.4 meters. And of course, the gravitational, of course, constant for this specific surface of the moon already is given in terms of 1.67 meters per square second, given as that one. So we are required to, of course, determine the time for the feather to fall to the surface of the moon. So in this case, we have looked at the various, so we're going to be determining our time the feather takes to fall to the surface of the moon. So in this case, we're going to look at the previous kinematic equations which we have, of course, been using by identifying our S given in terms of this specific description. So we have decided this is going to be S described in terms of distance. So it's going to be 1.4 meters. And then we have identified our G to be this specific value, but we're required to, of course, find this aspect of our time given us that one. So we're going to use, can use this specific equation. So the implication of this particular G, which are given in terms of a negative value, basically implies that this is going to be depicting the direction of motion of this specific object. So therefore we can find the time in terms of a magnitude, which is going to be found using this specific equation for the initial velocity times the time. So this is going to be motion along the y plus a half, of course, this particular value of a G times the square of time given as that one. So in this case, we are going to see that the initial velocity for this specific feather, which was related from this particular point, was basically equivalent to 0. So therefore, we are going to have this formula given in terms of a half a G the square of t given as that one, which is a half times 1.67 meters per square second given as that one, times the square of time, which is going to be given in terms of t squared. But remember that we had this specific aspect of S given in terms of 1.4 meters. So therefore, we're going to do an evaluation of this one, and therefore we're going to see that this basically is going to be giving us time in terms of seconds, whereby we're going to have this time as a subject. So since we have this information, I'm just going to do away with this. So we're going to have our time as a subject of this specific formula, whereby we're going to have the square of time given in terms of 2s over g. So we're going to have 2 times s, which is 1.4, and then we are going to have this specific aspect of g given in terms of 1.67 given as that one. So for us to find t, which is of course an absolute value of time, we're going to have the square root of that one, and from my end this is going to give me 1.67 seconds given as that one. So in this case, we are going to see that this is going to be assisting us in trying to evaluate the various problem sets which we are going to come across, especially in considering the kinematic equation which we have described from our previous discussion. So that is it for now, guys. Kindly check our description boxes for various links of other videos, and also engage us in the comment section and ring that notification bells to be getting updates on our various discussion in math and science. So that is it for now, guys. Bye, God bless you. Catch us in our next video. Sorry for that. So basically this one should be 1.29 from my end if I'm not wrong. So this is going to be 1.29 seconds basically, whereby this is going to be the root of that one. So in case you find particularly the difference in this specific value, kindly notify us in the comment section. So sorry for that confusion, but kindly, in case you find a different figure from this one, you can just notify us in the comments section so that we can do a rectification. So kindly check our description box, as I've said, for other links, and that is going to form a comprehensive part of this specific discussion. Bye for now. God bless you.